welcome everybody. So last time we spoke about electrochemical cells and the parts of an electrochemical cell and how to calculate voltage. Today what I want to start off with is, well, what happens if you don't have standard conditions? And so last time we dealt with an electrochemical cell that had zinc plus copper plus 2 ions yielded zinc plus 2 ions plus copper ion plus copper. And normally this was 1 molar and for the ions, 1 molar and 1 molar. But now we have a situation in which we might change those concentrations. Like let's say, for example, we had 0.1 molar Cu plus 2. And in that case, we would use something called the Nernst equation to figure this out. The Nernst equation looks at what the new voltage would be compared to the standard voltage if the concentration of the ions were different. That's where ln of Q comes in. Q is just the product, so Zn plus 2, concentration over reactance, Cu plus 2. Now, normally these would both be 1. So 1 over 1 would be 1. The natural log of 1 would be 0. And the E cell would be equal to the E0 cell. So that would be the situation that would normally be happening. But now we have a new situation. We change the concentration of Cu to 0.1. Well, what's going to happen here? Well, now we would have the Q being equal to 1 over 0.1. And now this would really be 10. And so now you would have the natural log of 10, which would be a positive number. And we don't really need to calculate what that positive number is. The important thing is that we are subtracting a positive number from the cell voltage that normally is there. So the voltage is going to go down. And so the idea is that when you change Q, the concentrations of the ions, and Q changes, you change the voltage. And here's the situation. If Q is less than 1, then that means that you really have more reactant than you're supposed to have. You're supposed to have 1 molar. And so this means that the reaction is going to shift to the right. And your voltage should actually be greater. If your Q is equal to 1, well then you have 1 molar of each. Q is equal to 0, and the cell voltage is what it should be. If the Q is greater than 1, like what I described up here, well then you have more products than reactants. And now Q is greater than 1, except that you're subtracting it from the standard voltage, and so the voltage will go down. Now, they test this concept down here still on the AP exam, but they don't expect you to know the Nernst equation. My advice to you would be to actually, memorize the Nernst equation and know it. And if you know the Nernst equation, then you can plug in values. It's not illegal to use it, it's just not part of the curriculum. Okay. When a voltaic cell reaches equilibrium, basically you have a voltage of 0. And you have a delta G equal to 0. And so at that point, there's no flow of electrons and the system is basically stopped. No work is being done. So let's talk about electrolytic cells. Electrolytic cells are kind of like the opposite of what we've been talking about with electrochemical cells. With electrolytic cells, you're actually taking electricity and you're causing a reaction to occur. And here I kind of, relate the differences between electrolytic and voltaic cells. One of the differences happens to be the charges of the electrodes. In a voltaic cell, the cathode's positive, anode negative, whereas in electrolytic, the cathode's negative and the anode's positive, and I'll explain why that's the case in a second. You can see differences with free energy, delta G, positive, so non-spontaneous and electrolytic, negative, so spontaneous and voltaic. And then the cell voltage. The cell voltage is negative in electrolytic and positive in voltaic. So again, that has to do with if the reaction is going to occur spontaneously or not. Now, here's an electrolytic cell that's actually used for plating, what they call electroplating. And so what I have here is I have a nickel anode. This is my more expensive or desired metal. And I'm trying to plate this piece of steel with nickel to coat it. And so what's happening here is the nickel normally would not oxidize. The nickel would be pretty stable. So what I can do is I can connect the nickel anode to the positive end of the voltage source, the power source. By doing that and turning the power source on, I am basically forcing the nickel to be oxidized. So the electrons will leave the nickel, they will go through the power source, they will be pushed out of the power source at the negative terminal, and the electrons will coat the steel. When that happens, the nickel that's in solution will attract to those electrons on the steel cathode and will be reduced. So some things to remember about electroplating is that, first of all, the anode, where the oxidation occurs, this is always the expensive metal. It could be gold, it could be copper, this is always the expensive metal. And it's positive just because it's hooked up to the positive terminal of a battery. Whatever you're trying to plate, so this is the object to plate, whether it be, a piece of flatware or just a piece of metal that you want to cover and make it look more expensive, that is going to be the cathode. And that's going to be negative. Now, this is one example of electroplating. We can practice more of these in class where we plate different objects just to go through it again. But let's talk also about other types of electrolytic cells where we're undergoing electrolysis. And the purpose of doing this is to try and isolate elements. And what I show you on the left here, this is actually molten sodium chloride. So it's a liquid molten sodium chloride. And that liquid molten sodium chloride is going to be oxidized and reduced, trying to isolate sodium liquid and chlorine gas. Well, this is a molten salt over here that I show you. And this is done industrially, and I'll show you a video of this too, where they take lead bromide and they do the same thing on a small scale. But look at what's happening to the sodium. The sodium is Na+. It's going to be attracted to the negative cathode, which is normally made up of graphite or some kind of very high melting point metal. And that is going to gain electrons and form Na. Now look, this doesn't happen. The voltage on this is about negative 2.37 volts, I believe. So that negative voltage means that it doesn't really occur. The chlorine over here, the chlorine's going to be oxidized, so that Cl- is going to form Cl2 plus 2 electrons, and that's also going to have a negative voltage. I think it's negative 1.36, I'm pretty sure. So when I go ahead and add up these voltages for this reduction and this oxidation of this molten salt, I get about negative 4. What is that? 13? Negative 4. Oh no, that's not. So that's 3, 7, and negative 3.73. I think my numbers are off a little bit. But the idea is that you have negative voltages. The overall voltage is negative for this process. It wouldn't happen unless I add electric current to this. So I would need to add electric current to this in order to get this to work. If I don't add electric current to this, it won't work. Now this is with a molten salt that I'm showing you over here. This is actually a pretty simple sort of setup. Although it takes energy to melt that salt and then energy to do the electrolysis, the purpose is to get these elements by themselves. Now, we could also do this with water, and we could actually take water and electrolyze it. We could take water and form oxygen, and we could take water and form hydrogen. The oxygen being oxidized, that is a oxidation, and the H2 being produced is a reduction. So the oxygen's made at the anode, the hydrogen's made at the cathode. Now what if I wanted to get NaCl and dissolve it in water and try and get the Na and the Cl out that way? I don't have the apparatus to heat up NaCl to about 1,000 degrees in order to melt it. I want to do this in a lab at school. And so the situation with aqueous solutions gets complicated. Because if I try to do this with sodium chloride, group 1 and 2 metals and aluminum, they won't be reduced like we have over here that I showed you with the molten sodium. It just takes too much energy in order to do that. But if we had something that had like cadmium, gold, silver, those also could be reduced. So those actually are able to be reduced compared to something like a group 1, group 2 metal. Halides generally can be oxidized, but fluorine cannot. And polyatomic ions, those cannot. Instead, you would get oxygen. Now, why is this occurring? Why is it the case where, you can't actually do this? And it has to do with the fact that the water is competing with the sodium and the chloride, or with the potassium and the iodide. And to show you this, I'm going to set up a little problem here. Let's say that I had Ki aqueous. Now, what happens is as follows. I would have, if things worked perfectly, my K plus would gain an electron and become K. And my I minus would lose an electron or 2 electrons and form I2. Now, if I look up the voltages of these, the K and the I2, we'll look them up and we'll see what they are. But we also have competing the water. And so the water could either be forming oxygen, like we have up here, or hydrogen. So I'm going to pause the video for a second. I'm going to look up all the voltages and rewrite those equations, and then show you what gets oxidized and what gets reduced. So what I did was I took a second to write down all of the reactions and their voltages in blue here. Now look, like I said, when we try and do this in water, then we have competing reactions going on. Up here I show you the 2 reactions that would be if we had molten K plus, I minus. So this would require to do this about, 3.5 volts, negative 3.45 volts in order to do that. But now we have a situation where we have this in aqueous water, so we have the water competing with it. So let's look at what's going on in terms of competition. So the 2 reductions here are potassium and the hydrogen from the water. Now look at their voltages. The voltage for the K is minus 2.92. For the water is negative 0.83. So guess what happens? The water is favored. So this reaction down here is what actually occurs. That's why a group 1 metal can't be reduced, because it just takes too much energy and the water is competing with it. Now let's look at the oxidations. Between I minus being oxidized and H2O being oxidized, it takes less energy for the iodine to be oxidized. And so what we end up having here is that the iodide will form iodine. And when you do this reaction, when you take Ki and you pass electric current through it, and I can do this in class for you as a demo, you'll see that the iodine, if we add a little starch, will form and turn black at the anode. Whereas the H2, as it forms at the cathode, will have bubbles from the H2 gas, but also if you add a little phenolphthalein, will turn pink. So sometimes the AP will give you these 4 reactions in an aqueous system and ask you, hey, what happens? What's going to be oxidized? What's going to be reduced? And the only way to do it really is to compare the voltages. And when you compare the voltages, you'll be able to figure it out. It's always the more positive voltage between the 2 reactions that will occur. All right, I'm going to stop here. Next time I'll do the quantitative aspects of electrolytic cells, and I'll finish up with redox titration and the Winkler method. All right, thanks so much for watching.